So, what is logistic regression? Usually, we have heard about linear regression and other type of regression. Usually, in our analysis, we usually take data and we start with a research question. And research question, usually, if it is a connection between or the association, or we are studying two variables, at least two variables, except in prevalence studies, there will be at least two variables. Usually, there is a dependent variable and an independent variable. So, we may be studying the association, so we may be studying the, or we are trying for a prediction. In all these situations, we need to find out the associations or what would be the value, the outcome value in a future patient. In these scenarios, we need to apply logistic regression. Here, actually, it is based on an equation, that mathematical equation we all know. We will come to that later. So it is actually a kind of relationship between independent variables and log codes of the outcome. Here it is very important. Normally, suppose we are modeling or we are studying on particular continuous variable, dependent. Suppose the dependent variable is continuous and the independent variable could be anything. In that scenario, actually, we are using linear regression because the outcome variable is continuous. But one of the issues with the categorical outcome variables, especially binary outcome variables like died or not, deceased or not, a complication occurred or not, that kind of scenarios, we have only a dichotomy, like, positive or negative, absent or present, yes or no. In these scenarios, we cannot apply this linear regression because it is a continuum. Linear regression. Here, the outcome variable is not continuous; it is a dichotomous variable. So here is the issue. How we can model this? Yes, so we have to think of now. We have to think of the equation like. There are like left side of the equation. Imagine this is a y. Imagine this is 1 second, please. Imagine this is what. Can you see this?
Yes.
Oh, 1 second, please. I think my.
Dr. Yadev, can you change the font color because yellow may not be very well visible?
Yes, I'll change. It must be visible now.
Yeah, that's fine. That's fine.
Okay. So y is equal to, can you see that?
Yes, it's clear. Can you see the blue ink?
This is the equation. So this suppose this equation is very simple things. Beta 1, beta 0, that is an intercept, and beta 1 you can accept as a coefficient for that particular variable. You imagine this x1, x2, x3, etc. as those columns in our Excel. Those predictor variables, especially those demographic variables, confounders, etc., etc. So you can imagine all these x's as various variables we take for the study based on the research question. And y is our outcome variable. So usually in linear regression, the outcome variable is continuous. But here in a dichotomous situation, like in a binary variables, suppose the death is the outcome, then you have two scenarios: died or not died. So we have only two options. So to model this, we cannot apply this linear relationship. So there should be some other way. So the problem with the linear equation is what we need in here is a dichotomy, yes or no. We cannot model that as such, but we can model the probability of dying or not. So the probability is bound between 0 to 1. So how can we model this one? That is a question. That is a fundamental question in logistic regression. How we can model the probability of dying or not dying. Here, one of the ways, or the best way is always the logit function. Logit function. There is a function called a logit function. Actually, the logit function is very simple. It's a log odds function. If you model the log odds of the outcome, then we can use the linear relationship between the independent variables. So we can actually use the equation. If the left side, instead of the y, if on the left side, it is a log odds y or logistic y. So probability of y, logistic, if this is the function on the left side, that means if it is the log odds y, then log odds of y, then it is easy to model this one. So actually it is an extension of the linear regression. It's also known as generalized linear modeling. So it can be considered as an extension of linear regression. It's a generalized linear modeling. So it is also known as GLM. Okay. So what we are modeling here is the logos of the outcome. So there is an interpretation question that comes out, but that is easy because we know how to interpret the odds and we know how to interpret the probability. So if we can model the probability by applying the link function logistic in the linear equation, that will be easy. That is a fundamental principles behind the logistic regression. So actually what happens is here the linear logos is actually we are modeling the logos of the outcome. That is very important. If the outcome variable is death, mortality, yes or no, or died or not, that means we are actually modeling the logos of mortality. So actually in the equation what happens is the y in the end result what we are actually looking for is the expectation of y. This is called the expectation of y. The expectation of y here in logistic regression is the probability of y. So when to use logistic regression? That is what we are discussing now. Whenever you have a dichotomy, whenever you have a situation, the answer is yes or no. So when you are taking the data, there is an outcome variable. It has got two levels. We code it as 0 or whatever we want. So there are only two levels. So we have a dichotomous variable, or a binary variable. In that scenario only we apply the logistic regression. That is one of the important things. So we have a lot of, in medical condition, these are the most common scenarios we have. We always end up with an outcome which is always most often binary. Now, you must be knowing all these things. What is a dependent variable, independent variables, then logistic function. We were discussing about this dependent variable. Dependent variable is on the left side of the equation, there is an outcome variable. This is also known as the dependent variable. Then this x1, x2, x3, etc. These are the independent variables. These are also known as, they are also known as the predictors. So we have two types of variables. It's a dependent variable and predictor variables or independent variables. So one of the so as a medical researcher, one of the easiest way to take data is designing the Excels or cobalt in such a way that you start with the first column. We usually start like this, this is Excel. We actually take the demographics first, then we take the other data. But it is always better from an analytic point of view. You always take after the ID, you take the outcome variables. Then the first variable you are going to analyze, or what is the most important variable in our equation. That will be the x1, x2, xi. Then you take the demographic. This is easy from a statistician or in a analyst point of view. So we already discussed how pardon. Pardon. Pardon.
So there was some difficulties. Yeah, over to you.
Okay. So this was what we are discussing about. The Z. Z is actually also this another word for Z. This is the right side of the equation. This is also known as linear predictor. LP. So here the Z is an actual combination. That vector is also combination of this one. So beta 0, beta 1, x1, beta 2, x2. This can be summarized as a Z also. So it's a combined linear impact of the all independent variables. Beta 0 is actually the intercept. Intercept means suppose when we plot, suppose is here comes the intercept. So beta 0 is intercept. That means if there was no other variables, all the levels of all x's were 0 not there, then or the null model, in that scenario you get the intercept. Though in that scenario, what is the outcome? Expectation of the outcome. That is that is dependent that is informed by the intercept. So independent variables are x and y1. We already discussed this one. Then coefficient. What is a coefficient? Coefficient is actually the weight. So that is the mathematical formula. This is what we are estimating when you are using the logistic regression. If our research question is an association study, it is very important. Sometimes we get confused between various kind of studies, and we apply the logistic regression. Logistic regression applying two scenarios. that is applied in association studies as well as in prediction studies. So we need to differentiate which study we are going to do. What is our research question? Is it an association study, or is it a causal study, or is it a prediction study? It's very important when it comes to logistic regression, because the modeling approach, the variable selection approach, the model specification, model fitting, everything is different when it comes to prediction versus association studies. We'll be concentrating more on those technical aspects, how you can select the variables, how because putting all these variables in a software is easy at now. You don't have to manually calculate all those things. Various softwares are available. SPS is available, Jamovi is available, JASP, or you can hard code in R or Python. So getting the result is not that important and not that difficult. The most important thing is how you design the study, what is the clarity about the research question, and what is the approach you take for take at the time of analyzing. So, so what happens in I told you the probability is bound between 0 and 1. But the linear predictor, it should be between minus infinity and plus infinity. So actually, this this p minus 1 by p is actually, that is an odds. Odds is bound by 0 to 1. So when you take the log of odds, actually it becomes minus infinity to plus infinity. So logit p actually can be used for
Dr. Yadev, sorry to interrupt. Anita here. Some of us may not be able to understand the specific terminologies. So just requesting you to make it little simple, the formulas, so that we understood up to here that outcome variable is the dependent variable, and the factors that determine the outcome are the independent variables that we till now we understood, but the formula and logic transformation is getting a little difficult. So requesting you to make it simple.
Okay. So actually, the problem in a binary prediction or binary association studies is here we have a question of dichotomy. Here we have only two levels, yes or no. This is not a continuous. It is not bound. It is bound between. If you take the probability of this outcome, it is bound between 0 to 1. But when you are approaching, when we apply the same linear equation here, it is not possible to get the result. So you need to convert this into a logic some function, some other. You have to transform this. This particular transformation is not logistic transformation. Logistic transformation. Is it okay? Logistic transformation. So how you can convert this normal thing to logistic transformation? That is a question here. So what is logistic? Logistic is very simple. Log odds. So log odds is logist function. Okay, log odds. So if you take the log of odds, what is the odds? If you cut an apple, there are two parts. So that the first part divided by the other part, that is the odds. Actually, the original intuition should have been odds, but we are more tuned to probability when we become more and more educated. So the odds is actually p by 1 minus p. That is okay for all of you. We all know odds now. Yes, it's okay. Yes. So this p.
I'll let the others respond. Yeah.
So the p divided by 1 minus p is the odds. So we have the odds. The odds can be from 0 to infinity. Is it not correct? But probability can be only from 0 to 1. Okay. Yes or no. And the probability. So it is bound by 0 to 1. But the odds is bound by 0 to infinity. That means the odds can be up to infinity. But still we are having only right side of the continuum. Continuum. That means 0 to infinity. We should have minus infinity also here. How we can convert this to minus infinity? You just take log of odds. When you take the log of odds, you will get this whole continuity you will get. Okay, that was how the link function came. Logistic transformation. This is called a logistic transformation. This is called a log odds. So what we are doing at now is we are taking the log odds Okay, this is also written like logit P. The same as log odds. Logit P means logit of the probability means log of log odds. This is odds. So log odds. So log odds is bound between minus infinity to what plus infinity. So you can use the linear equation. You got it. Is it okay now, till now? Is it okay till now?
Yes.
Actually, we could have avoided all this. We don't need to know all these things and all. We just need to know how to design the study, how to select the variables, etc. That will come to later. This is the only maths we are discussing here. So the purpose is this one. But actually, our purpose is what? It is not the log odds. We need to find out the probability, because the probability of dying is how much? Is it 70%, 60%, 40%? We cannot say yes or no, because it is that concrete thing we can never, that deterministic thing we can never reach it. So we can tell about the probability of dying, probability of having that complication, probability not having that complication. So actually we are interested in probability rather than the log odds. So how we can use the get the probability? We model the outcome variables and independent variables. I said we model the dependent variable, that is the outcome variable, and what do you call the independent variables, also known the predictors, using log odds. So when you use the log odds, you can use the same linear equation. But we are not interested in the log odds of P. We are actually interested in the probability. So, but it is a mathematical equation. You can just use another formula, that is this one. We can find out the probability from this equation. So these two equations are the fundamentals of fundamental maths behind, or the basis behind the logistic regression. I think you would have followed this much. Okay. Should I explain more?
This sounds
Anybody?
clear so
Yeah,
far.
please go ahead. Please go ahead, sir.
Okay. In in graphically, when we are plotting linear regression, actually we get something like this. This is a x, this is a y, or this is the z, or what do you call this, predictors or independent variables. These are outcome variables. This is a continuous variable in a what do you call in a linear regression. There we are trying to predict this y, actual y. So at a point of x, you have a y. So this is what usually happens in linear regression. But you will not get this kind of modeling approach, or this kind of continuum or model fit, best fit line in logistic regression. Instead of that, you need to model 0 and on. This probability bound between 0 and on. So here the outcome is bound between 0 and on. So the fit line will be like, because this area you have 0, this area you have the, in between you have the probability. So this is a graphical representation. We can forget about this sigmoid curve and everything. That is just the graphical representation of what we are discussing till now. So actually what we were looking for is the log odds of the outcome, log odds of the outcome, log odds of the outcome. No, actually, the log odds of the probability outcome was not we were looking for. We were actually interested in probability, but that can be mathematically found from this. So this part you will get this Z part you will get from the equation, or after the analysis you will get this. So you put in this, you will get the probability. Now, when we discuss the next part, it will be very clear. We will go to next part. Now, so far, we have discussed about the fundamentals of logistic. What is the basic difference between linear regression and logistic regression, and how linear regression, logistic regression can be considered as an extension of the linear regression, or it is also known as generalized linear model. And the same linear predictors combination of predictors we use. There is no non-linearity component there. We can use that linear thing by using the log odds of the probability of y. When you are using the log odds, what usually happens is we can easily model that using the same linear equation. But we are not interested in the logos. We are actually interested in the P. The P can be found from the equation I just mentioned. So this is the fundamentals. Now we come to the model building and the various issues related to the logistic regression. This is the most important part, because when we were starting with the logistic regression in 2009, 10, etc., we were just putting everything in the SPS and coming out the result without knowing the fundamental philosophy behind model building, etc. Actually, this is very important. This is what we need to know, apart from rather than the mathematics. And now we know why we model that way, and what is the situation when we need logistic regression. Logistic regression is needed whenever you need to model the probability of finding a probability of outcome variables based on some independent variables. Okay, but there is a catch. Is it a prediction or is it an association? These are two important things when we need to know when we apply the logistic regression. There are two types of studies. One is the association studies. The extension of the association study is the causation. So for that, you need another modeling approach that we will, if we have time, we will discuss in another class. So the association studies, one type of study. Another study we use logistic regression is the prediction. Most of the softwares and most of the algorithms in logistic regressions are actually planned for prediction. But in medical research and epidemiology, most of the scenarios we apply logistic regression is for the association studies. We will discuss what are the differences between these. And for now, I will just say what are this one example of the association study. What are the risk factors? What are the risk factors of carcinoma lung? So here, how do you model this? Carcinoma lung. So the outcome variable will be probability of logos of probability of carcinoma lung, yes or no. That is a Y. But the right side of the equation, you have the beta 0 plus beta 1 age or something like a lot of things. Excuse me. So these are what we are interested in. Are we trying to predict carcinoma lung? In risk factor studies, actually, we are not trying to predict. Here in medical research, when you are studying the risk factor studies, actually, we are interested in the beta 1 plus beta 1, beta 2, etc. That means we are more interested in the effect size. What is the effect of this on? This is what we are studying in association studies. What is beta? It is actually the change in Y with respect to change in X. This is what medical research is more concerned about, rather than predicting the Y. This is very important. So in association studies, there are different types. It could be risk factor of a diagnosis. It could be prognostic factors of a complication. So it could be like something that precedes our outcome. So when we are studying the risk factors, actually in the equation side, we are actually on the right side of the equation. Here we stand. And we are more concerned with betas rather than Y. And we have you can imagine like this. When you are studying the risk factors of carcinoma lung, you are planning the study such a way the Excel contains one outcome variable, carcinoma lung present or absent, then demographic variables, important demographic variables, then what the most important risk factors you have, then the confound is also. So here, actually, we are not concerned with the future patient getting carcinoma lung. We are actually concerned with what is the effect of smoking on lung carcinoma. So we are actually on the right side of the equation. We give more importance to beta. That is a fundamental difference when you apply the logistic regression for prediction versus association. Most of the medical studies is not concerned with prediction. Most of the studies are concerned with the risk factor studies or prognostic factor studies. That is merely association studies. So in that scenario, we give more importance to beta, but we are not concerned with beta as such. We take the exponentiated beta, that means the odds ratio. There comes the interpretation of odds and confidence interval. So here the most important is actual value. We should get the correct beta 1, beta 2, etc. because we want to interpret that beta. In prediction, that interpretation need not be there. So these are fundamental difference. Are you with me so far? Please. Am I still with you?
Yes, Dr. Yadav. Yes, Dr. Yadav. This example of lung cancer and smoking and other factors, that is helpful. If we can understand it through a clinical example, that is useful. Thank you so much.
So now onwards, we will not be discussing about the mathematics behind all this. We will discuss about this conceptual concepts only. Okay. Now the same example. We have a few variables called the predictors or independent variables. With the most, our research question is suppose our research question is something else. Is smoking associated with carcinoma? The first question was, what are the risk factors of carcinoma? Now the research question is smoking associated with carcinoma? There could be another question. Is smoking a causative factor for carcinoma? The third thing, it is very difficult to come up with the present thing, but we can have with various new methodologies. So we will not be discussing about that. That will be for another class, causal modeling. Now, the associations only we will stick to. Suppose the second association study is smoking a risk factor of carcinoma? Here, what is the most important variable? Smoking is the most important variable. So, carcinoma lung, smoking. But we know that there are a lot of other variables which can influence this relation. Those are called confounders. And then there are some covariates also. We need to take into account these things, because this may be associated with the smoking and this may be associated with the carcinoma lung, and these variables are not in the pathway between smoking and lung. So these are the confounders. So if you want to isolate the effect of smoking, here the research question was this one. Is smoking associated with the carcinoma lung? In that scenario, it is not like the risk factor study, though we use the logistic regression. Here, the most important thing is finding out all other covariates and confounders which can influence this relation. And we need to isolate out these things. Here, what we are doing is, you need to know that here the exon should be smoking. So here comes the importance of specifying the variables. Which one is the first variable? This may not be that important prediction, but this is very important when it comes to association studies. So in the nuts and bolts of logistic regression, these are the important things. So exon should be the smoking. The other confounders or covariates you put in the model, that comes after that. How many variables you put in the equation, that comes later. That is a variable selection part. So here we need to know the theoretical knowledge, the status quo regarding the literature. Then only we can model this. So this is very important. Here the beta 1 we interpret. So the model is like that: beta 0 plus beta 1 smoking and plus beta 2 something like that. So when we interpret, we are interpreting only the beta 1, but all other things. So we will be interpreting like with the smoking, with all other variables remaining constant or kept constant. That means x2, beta 2, beta 3, beta n. All other variables kept constant or kept constant, keeping constant. What is the effect of smoking on carcinoma? This is given by beta. The interpretation of beta is like this. This is the effect of delta y given beta delta x1 given all other variables. That given all other variable is very important because keeping all other variable constant, what is the effect of smoking? In that scenario, beta 1 interpretation is very important. In that scenario, never try to interpret beta 2, beta 3, etc. Because in that scenario, beta 2, beta 3 will be direct effect, not the total effect. This particular thing is called a table 2 fallacy. We will discuss that in some other scenario. Okay. So association study, there are two important things. Is it a risk factor study or is it a pure relation between one variable and outcome variable? This we need to be very clear about. The same risk factor study, carcinoma lung with 5 variables like smoking, age, asbestosis, or some other variables. We have, imagine we have some 5 variables or 6 variables. Now another scenario, prediction. We want to predict a future patient when he comes, whether he has got carcinoma lung or not. It is like just like a diagnostic test. In a future patient, we need to know whether when he comes to my OP, I need to know whether he has got carcinoma lung or not. This is a prediction question. This is also known as a classification question in machine learning. Here, what we are doing is actually we are using the same logistic regression, but we are applying it in another way. Here you can imagine the Excel like this. On Excel, ID first column, second column, you have the outcome variable. Then you have the 5 x1, x2, x3, 5 ages, sex, something like that, 5 variables. So you have the total X with what you call the outcome variable. Death, this is outcome variable, this is x1, x2, etc. Now you create an equation. You know that that particular equation from the logistic regression, you can calculate beta 0, beta 1, beta 2, etc. So you can easily derive an equation, full equation, y is equal to some value 1.2 plus 3.1 into smoking or something like. You can come up with an equation like this. So here the studies, purpose of the particular study is to come up with the equation in prediction modeling. Come up with the equation. Now you have the equation ready. Now that equation can be converted to a score, or the equation can be fed into a computer algorithm, or it can be converted into high risk, low risk, or it can be something like an app, or it can be a web page with a prediction web page. Now a future patient comes. We suspect carcinoma lung, but now we have the actual value, age, the particular patient. That age become a constant value. That means it is no longer a variable for that particular patient. The age is particular value. So now that means we have smoking plus or pleasant or absent, that 1% plus 2.1 into age. We have the actual age at present, though that is a constant. So like that, everything is a constant now. Now we can have the Y. This is the prediction. Have you got the difference between prediction and association? Yes, sir. Hello?
Yes, Dr. Yadav.
Yes.
Yes, Dr. Yadav.
The same question, the same scenario, the same variables, but two purposes, entirely different purposes. The first two questions were, what are the risk factors of carcinoma lung? There we are concentrating more on the risk factors, more, or what are the prognostic factors, what are the predictors. Here we are more concentrating on the independent variables. That means we stand on the right side of the regression equation. There, more important is the coefficient. That means the beta 0, beta 1, beta 3, etc. But this is exponentiated to get the odds. So we interpret the odds. So the actual value of the odds is very important. Odds ratio is very important when it comes to association studies. But in a prediction, we use the same format of Excel. But that is not for finding out the effect of the particular age or smoking. It is to in the future, we need to predict the Y. But unless you have the equation ready, you cannot predict. For to create that equation, you use that logistic regression and the Excel. Now, when you have a equation ready, that means beta 0, beta 1, beta 2, beta 3 ready. When a future patient comes, we just For that particular patients, all these 5 variables on the right side equation will be a constant. Age, I know this particular patient is 50 years. I know this is a male. So the male, we code it at 1. So I put it at a 1. So he is exposed to asbestos or not, like that. So for that particular patient, already we created the equation by some investigator, and he has it in the form of a equation or a score. Score means in this converting this 1.2, 3.92 mathematically easily to calculate whole value. Upon a whole value to when you convert that, you get a score. But you don't need a score at present because you can we have the computational power. We can feed the equation to some web web interface, and you can come up with the result, or mobile app. So this is a fundamental difference between associations